I've got a good pointer. What kind of pointer do you have?
The backup one that you used last time.
You know the.
This one. It's a flashlight.
Oh, this will work good. Yeah, this is real good. The New York Times had an article. Was there a question? Okay. Oh, okay. So I'm Chris Morris. I came to New Mexico in 1973, and I met the two Bobs here about the time I came up, which tells you all we're pretty old. I worked at Los Alamos, and for a long time, I worked studying these mysterious particles called pions using the LAMF accelerator, the Los Alamos Meson facility. And while I was doing that, people would say, well, you know, I studied nuclear physics with pions, and people would say, why do you study nuclear physics with pions? That sounds not very useful for anything. And at the time, the best answer I had was, why, just because you learn new things and it makes you think. And that's absolutely true, and that's why people do science, is because the way, when you look around you, there's a world out there. I'm a physicist. What makes the world work, I mean, people look at the world and they use physics to try to analyze it and figure out why things happen the way they happen. And from the time physics started, when people like Galileo started looking at the orbits of planets around stars, I'm sure that those people always thought that what they were doing was, you know, nothing that anybody would ever be interested in. But then, you know, some theorist comes along, you know, 50 years later and writes down some theories, and some new framework to understand things is invented. And so once you understand things, you can build cars, and you understand how things fall, and all the practical things around you, electricity, all come out of this very obscure science people do. So I'm going to try to make that connection tonight a little bit, and I'm going to try to do it with these demonstrations. And so the first 5 minutes of my talk is really going to be most of the talk. So what I've done, the practical thing that I've done with the things that I learned doing basic science in Los Alamos have involved, they're nuclear weapons related. They've involved using different kinds of radiography to look inside of things. Los Alamos has a history of doing this, and I'll tell you a little bit about it. These are some of the radiographs that we make using charged particles. We use the proton beam from our accelerator to look inside of things. This is looking inside a piece of metal, and this piece of metal is a piece of tin. And down here, there's a little tiny puck of high explosives, just a little piece of high explosives. The high explosives is detonated, and it tries to push the back of the metal into the front of the metal, and it makes a shock wave. And you can see that shock wave going through the metal over here. By studying these shock waves, you can understand metals at very, very high pressures that you can't get any other way. The same kind of radiography here is making a movie of this little watch. So this movie was made taking 5 million frames a second. And this movie over here was taking 2 frames a second. And you can see the little balance wheel here spinning back and forth, and you can see the second hand moving around. Now this movie is only about 10 seconds long, so that it jerks and starts over, just like this movie does. And this isn't a movie over here, but this is just a radiograph using the same technique. Here we used 800 MeV protons. MeV is a unit of energy that us nuclear physicists use. A volt, the energy a charged particle gains when it goes across a volt is 1 electron volt. So this is 800 million electron volts. This is kind of an interesting energy because it's not too far away from the mass of this particle that you accelerate. A proton has a mass which is equivalent to an energy of about 940 million electron volts. This is low energy electrons. In terms of the electron mass, it's a lot higher, but this is a relatively lower energy, and so this is a fishing fly. So we can radiograph things. But now I need to change my slides, so I need this device, and I need to go forward. Okay. Oh, point it that way, and go forward, or go forward. Well, that's not going to work. Somebody's got to show me the right button. Up. There we go.
Point it this way.
Yeah, but I have the menu up, and it's not doing anything.
We can manually advance it if you want to.
Oh, here, this will work. If I get that there, and then I hit Enter. I hit Enter. I hit how do you okay.
Down takes the next slide.
Okay, I got it now. So, radiography started with X-rays. X-rays, back in the 1800s, people started to study electricity. In the 1700s, people started to study electricity. And then about the middle of the 1800s, it was all brought together by a guy by the name of Maxwell. And he figured out that there are electric fields and there are magnetic fields, and they're all coupled together. And when you have combined electric and magnetic fields, you make radiation, and you can make radio waves. Radio waves are shown on this graph here. They're electromagnetic waves that have a long wavelength. They can have wavelengths that are kilometers long, and they can have wavelengths that are meters long. As you add energy to these electromagnetic waves, you move up this scale, and you go through microwaves, infrared, visible light. It's all the same radiation. And then as you go higher in energy, you get to X-rays and gamma rays. And we all know what X-rays are. There are these high-energy electromagnetic waves. People didn't know that they knew they could make radio waves, and they understood that light and radio waves were connected. But in the late 1800s, people were studying electricity in a different way, and X-rays were a discovery. People didn't know that you could make radiation that short in wavelength. And the man who did that, that way. I want to get this down. I'm an experimental physicist, trust me. There. This man, Wilhelm Conrad Röntgen, he, in some sense you can credit him with starting the field that I was in, which is nuclear physics. He discovered X-rays in 1895. He was doing an experiment with a tube that looks like this. Through the late 1800s, people spent a long time trying to get to ever higher voltages. And one of the tools they used was a thing called an induction coil. This is an induction coil. So if everybody can come up here, I'll show you this thing. This is a little transformer, and it's got a little iron core that comes out the side. And when you put current through this iron, it turns into a magnet and it pulls that little connection off of this pin, and that makes a little pulse of electricity that goes into coils, a primary coil around this induction coil, and then there's a secondary coil, and you can make a high voltage this way. So the voltage this is making now is probably about 6,000 or 7,000 volts. So this is what people had for electricity in the late 1800s. The electricity in the wall wasn't installed yet, so they had batteries. And so this is a battery. It's 3 volts. It goes into here. And this 3 volts turns into thousands of volts across here. Now, if I were to plug this in here, I would double the voltage that I have across here, and I could open this gap to about twice as wide. So that's how you make high voltage, and that's how Röntgen was making high voltages. This is a tube that's called a Crookes tube. And it is something that Rankin knew about and people were using to study at the time. They discovered that if you take a tube like this and you pump the gas out, if you pump the gas out to where you have about 1/100th of atmospheric pressure and you put a voltage across here, the gas glows. And then this man called Crook discovered that when he got a better vacuum pump, he could pump more gas out. And as he pumped the gas out, the glowing in the tube went away, but he began to see a glow on the front of the tube. And he figured out that even if he put the electrode down here and up here, he still saw a glow on the front of the tube. So he called these things that he saw in here cathode rays. So I'm going to show you that glow. So these cathode rays, people didn't know until after Rankin discovered X-rays that these are electrons. That in the little bit of gas that's left in this tube, and the pressure in the tube is about 1/1,000,000th of an atmosphere, cosmic rays or natural radiation come in. That makes some ions. You have ions and electrons. And the electrons get accelerated towards this voltage, but they're going straight, so they continue to go to the front of the tube. And you can see you can make a shadow of things in the tube. So people had worked with these tubes and they knew these electrons could make some materials glow, and they could make materials glow, they could make shadows of things. And they had just started to try and get the electrons out of the end of the tube. So Rankin was trying to get electrons out of the end of the tube, so he built a tube with a thin window, and he covered it over, and he was going to try to use a phosphorescent screen, a mineral that glows when it's excited, to see these electrons. And he just noticed that when the lights were all off in the room and he was tuning his apparatus, his phosphor screen sitting over here was glowing. And he wondered why that was, and so he started putting things in front of it, and he discovered that the thing that made the screen glow, the particles or whatever it was, would go through material. And he did this in November, and within a couple weeks he worked night and day because it was so exciting. He was seeing through things that you can't normally see through. He found out that he could make X-rays of his hand. He made a famous X-ray of his wife's hand. So that was a remarkable discovery. He discovered X-rays and he invented radiography all in the course of a couple of months, doing fundamental basic research that almost immediately had real practical applications for solving people's broken bones and looking inside people to do surgery and stuff. So that's how radiography started, with a simple little experiment that didn't look much different than this. The apparatus was a little fancier. The battery was probably not as nice as this, and the tube was very similar. So he invented X-rays, and rays were on their way. People knew they had cathode rays, and then X-rays were discovered, and people started studying X-rays. The next person, don't leave, but you can look up at the screen. I'll try and change it here. So that was what Conrad Rankin did, and he got, for that, he got the Nobel Prize in 1901, and it was the first Nobel Prize that was given. Let me try and make this go to the next thing. Okay. I'm sorry.
Just seem backwards. The shadows.
And the mechanism by which it works, you put high voltage across the tube, you put a positive voltage on the anode, a negative voltage on the cathode. And so people knew that that negative particles push against each other, they repel each other, so electrons are pushed away from the cathode and they make this glow on the front of the screen. This is not reliable, so I'm just going to go back here. So, this man at the top is a man by the name of Becquerel. I don't know how much science you've studied, but Becquerel was studying X-rays from a Crookes tube. And he had a laboratory, and people were trying to measure the properties of X-rays. Again, in about 1897, so a couple of years after Röntgen had first discovered them. Röntgen was in Würzburg in Germany. Becquerel was at the Sorbonne in Paris, France. And in the process of studying these X-rays, he was using a phosphorescent screen that had some uranium in it. And he put the phosphorescent screen in his desk drawer next to some film, and he found out that his film had been fogged by the phosphorescent screen. And he started studying that, and he found out that there was radiation coming from this material, which was uranium. And so he discovered a new kind of ray. He didn't know quite what to call it. It was called uranium rays for a while. And so he was at the Sorbonne, and so was Marie Curie and Pierre Curie. Now, Pierre Curie had invented, his claim to fame was he had invented a device which was a sensitive electrometer. People built these kind of electrometers, which are called gold leaf electrometers, a long time ago. Pierre Curie had invented a more sensitive one. So Marie Curie, this lady here, who really started nuclear physics, decided to look to see if this radiation ionized air by hooking up an electrometer. And what she found is what I'm going to show you here. So I don't know if you need to come up here to see this or not, but when I take a high voltage and I charge up this electrometer, this little gold leaf jumps away from that little stainless steel rod because like charges repel each other, and I just put a bunch of charges down here on this electrometer, and so that gold leaf pushed away from the metal rod. If you do experiments in school, you probably know about pith balls. And I just charged up 2 of these, and we're going to do Marie Curie's experiment. This is a plate that was made from before World War II. It's got this beautiful orange color because the glaze has got uranium oxide in it. It's natural uranium, so it's radioactive. And so I've charged these up, and these little gold leaves came up to about the same number on the dial. And we're just going to walk away from that for a little while, and we'll come back later and see what happens. But Marie Curie found out that uranium was radioactive. She coined the term radioactivity, and she measured very carefully the radioactivity from uranium. And she did a whole set of experiments where she made the uranium different chemicals. So she used uranium oxides in different states, pure uranium metal, and different quantities of uranium. And by doing very careful measurements, she showed that this radioactivity was a property of the uranium atom. It didn't depend upon the chemistry or anything else. And she also went through all the chemical elements that she could get samples of and found that there were 2 radioactive elements of the things that had been discovered so far. There was uranium and thorium. And so for that, she was awarded the Nobel Prize in 1903. And since she was a woman and people didn't think women could do science, it was shared with Becquerel and her husband. But she did most of that work. I mean, women in the audience should be proud of the work that she did. She was actually a very careful scientist and started the field of nuclear physics. And she was also the first person to win 2 Nobel Prizes. Next view graph, please. She did, well, she found that uranium was radioactive and thorium was radioactive. What's that? Thorium, I think. And then she went on. She went on after she got this Nobel Prize in 1903 in physics. In studying different uranium ores, she found out that different ores had different amounts of radioactivity in them. and she thought there were new elements in them. So she did careful chemistry, and she went on to discover polonium, and she didn't, I think she shared the discovery, no, she discovered radon, I think. And for that, she got the Nobel Prize in Chemistry. So she was the first person to get 2 Nobel Prizes. So next view graph, please. And then finally, this guy, Victor Hess, he didn't get the Nobel Prize till quite a lot later. But it wasn't long after these Nobel Prizes that he did the research that gave him the Nobel Prize. That research is kind of demonstrated over here, and it will be demonstrated over here after we wait for about halfway through the talk. These electrometers will discharge, and they discharge because of radioactivity. This one will discharge because of natural radioactivity. This one will discharge because of the radioactivity from the uranium plate. And so people couldn't get electrometers that were filled with gas not to discharge no matter what they did. Hess did a bunch of heroic experiments. He took electrometers, he flew on hot air balloons, and he flew at night in hot air balloons, he flew during the day, he flew over lakes, he flew over the ocean, and he determined that part of this radiation wasn't coming from the Earth, it was extraterrestrial. And so that was the discovery of cosmic rays. And for that, he got the Nobel Prize in 1936. So these are 3 Nobel Prizes, all from simple experiments that you see here, discovering radiation and studying the properties of radiation. So this demonstration here, which you can see on the wall, uses more modern equipment. And later on in my talk, I'll talk a little bit about this stuff. But if we set this thing up, this is an oscilloscope. And I have some electronics here, and I have 3 detectors here. So this is 1, 2, 3. And I just set it up so if I see a signal here or I see a signal here in the top one or the bottom one, it draws a trace across the scope. So when I set my uranium plate next to the top tube, you can see it counts faster. When I set it next to the bottom tube counts faster. And if I put the uranium plate over here, there's still a lot of radiation, and a lot of that radiation is coming from the floor and the walls and the concrete from just radioactivity. And the radioactivity, a lot of it is because of uranium, and some of it is because of cosmic rays. When I require that the top tube and the bottom tube see something at the same time, which I just did, you can't tell that now, you see pulses in all the tubes. You see the middle tube, and that's because these are on a line. If I take this middle tube out of the line, that's the blue one, you see that the blue trace doesn't show signals any longer, and when I put it back in there, you see signals. So what are those? That's what Hess studied, and what those are charged particles that are coming from the top of the atmosphere. And they're a kind of particle called muons, which are not so far from the particles that I came to Los Alamos to study, which were pions. In Los Alamos, we have an 800 MeV accelerator that accelerates protons. In the universe, there are sources of high-energy particles, a lot of them are protons, that are flying through space. In Los Alamos, we would take those protons and shine them into a target full of carbon nuclei, and that would liberate from the nucleus these things called pions, which are the particles which are to nuclear physics like electrons are to atomic physics. In atoms, in molecules, you bind atoms together by having electrons hop back and forth between the atoms. In nuclei, you bind neutrons and protons together by having pions hop back and forth. So when those high-energy particles hit the top of the atmosphere, they collide with nuclei, and they make a lot of these pions. The pions have a short lifetime, and they go away because they interact with nuclei in the atmosphere. When the pions go away, because of decay, they turn into muons. These muons don't have any nuclear interaction, and say they come all the way down to sea level. And these are the particles we're seeing here are muons. So I'll talk a little bit about muons later on. So, next view graph, please. That's what this demonstration was. These are tubes. In the middle of each tube, there's a little wire running down there. When these particles, a muon, an energetic charged particle goes through the gas in the tube, it makes ions, just like we're doing over here with this uranium plate and like Marie Curie used. The electrons from those ions are collected on that wire, and as they go to the wire, because of the electric field, they get amplified, and that makes a pulse, which comes out of the tube, which is what you see here. So that's the physics that people did around the turn of 1900 that I'm going to use for the rest of my talk. So next view graph, please. So this is, that may be the, I don't know what view graph this is. So this is Wilhelm Conrad Röntgen. I know what this is. This is a radiograph he made before he published his first paper in Nature, sometime in the period between November of 1895 and January of 1896 in Würzburg, Germany. So the hand of an autonomous Germach von Kohler or something like that in Würzburg. So that's a man's hand with his wedding ring on it. And this was the first time people had seen inside of opaque objects. I mean, that's pretty remarkable. This caught people's imagination immediately. Next slide, please. So this is a radiograph that was made in February of 1896, you know, just months after the discovery of X-rays. But this was made at Columbia University in the United States in New York. This is a hand of a lawyer who had gotten shot in his hand with a shotgun. So these are shotgun pellets. And this was the first radiograph that was used surgically. The surgeon used this to locate the pellets and pull them out of this poor guy's hand. That must have been painful. And this radiograph was made with a tube look probably like this, a little different configuration of electrodes inside, running at a higher voltage, with this man's hand sitting out here and a piece of film behind it. It was as simple as that. Didn't have to plug it into the wall. No fancy stuff, just all simple things. Next view graph, please. So why is Los Alamos interested in radiography? During World War II, a bunch of people came out here, eminent scientists from Europe mostly, some from the United States, came to New Mexico on the Mesa Los Alamos is on, and their goal was to build an atomic bomb before the Germans or the Japanese built an atomic bomb. They took this very seriously, and people had calculated that if you take enough uranium and put it in one place, you can make a chain reaction and liberate a lot of energy because of fission. So in this little movie over here, these green things are meant to be uranium atoms. The little red things are meant to be neutrons that come when you split the uranium atom. Uranium has extra neutrons in it. When you split it apart, you like to make two nuclei that are roughly half the mass of uranium. But in order to have those nuclei be stable, there are neutrons left over. So in this case, each atom that gets split is liberating two neutrons. Pretty early on, after people discovered this process called fission, they speculated if you put enough uranium together in one place, you would see the following. Next view graph, please. Oh, we have to hit it again maybe. There we go. So here, there are more uranium atoms and they're closer together. So now, these neutrons almost always hit another uranium atom and you get a chain reaction. This chain reaction, these neutrons are going very fast. They're not going the speed of light, but they're going 1/10 the speed of light. So this releases a tremendous amount of energy very quickly because each of these fissions gives up 200 MeV of energy, so almost the mass of a proton. So in terms of E equals mc squared, the energy is huge. And so this generates an explosion. So the way you build an atomic bomb is you take two pieces of fissile material, uranium-235 for instance, and next view graph, you slam them together. This makes a supercritical mass. You put some neutrons in and you get a chain reaction. And so in Los Alamos, the first attempt to build an atomic bomb used uranium-235. And it was pretty well understood because there's uranium-235 in nature. But it was very hard to get the uranium-235 out of this uranium because it's only a small fraction and it doesn't look very much different from the other uranium isotope that's in that uranium-238. And so it takes a huge industrial plant. So people early on discovered a new element. They built a reactor to make this new element called plutonium-239. This is an element that doesn't occur naturally, but you can make it in a reactor by taking one of these neutrons, capturing it on the predominant isotope of uranium, uranium-238, and that beta decays and turns into plutonium-239. So there was a plan to build two different kinds of atomic bombs in Los Alamos. One used plutonium and one used uranium. The plutonium bomb was really very problematic. When they started getting enough plutonium, plutonium makes its own neutrons. And so when you try and assemble it like this, it goes critical before you get an assembly, and you don't get an explosion. You just get a big flash of radiation. They had to put the plutonium together more quickly. The way they did that was by using an implosion, by putting explosives around the outside of a sphere of plutonium, and then next view graph, please. Detonating the explosives and compressing the plutonium. This is hard to do. If you take something and you try to compress it, it wants to squirt out. If you don't do this exactly right, it doesn't work. And so the scientists needed to come up with ways to make this implosion work. And that's when radiography became important in Los Alamos. Next view graph. This is an early experiment called the Rala experiment. One of the experiments that was used, it's a radiographic experiment of a different kind to tune this implosion. They had just built reactors, and reactors made huge amounts of radioactive material. Marie Curie worked for years to generate small amounts of radium that could be used for experiments. I mean, and she could get, but it was very radioactive. Those were the hottest radioactive materials people used before reactors. After reactors, using this fission process, you could make huge amounts of radioactive material. So the scientists took a source of radioactive barium from a reactor, which turns into radioactive lanthanum, and this is one of these sources, and these people are out here pulling on this thing from a long ways away to stay away from the radiation. And this is a cast that the source is in. They took a source out of this cast and put it in the middle of one of these implosion devices, not with plutonium, but with some other kind of metal around the outside, and they measured the radiation that made it to the outside as this was being exploded. So next view graph. This is what this experiment looked like during the war. And if any of you are from Los Alamos, this happened down in the canyon about where the sewage plant is in Bayo Canyon. This is high explosives around a metal core, which in this case was cadmium, and these are the detectors that measure the radiation. Next view graph. This is what happens when they detonate the whole thing. This is an explosion. It makes a thing called a jet where a lot of the energy goes up in the air. Next view graph. And this is what their data look like from these implosions. They measure the number of gamma rays that come to the outside as a function of time. This is a scale on the bottom in microseconds. And this is the heavy metal being compressed. And this was a successful implosion. This is how they developed the techniques that made the Trinity experiment work. Next view graph. The other kind of experiment they did was more conventional radiography. This doesn't look like it, but this is an electron accelerator, which is called a betatron. This was an accelerator that was invented. This is an electron accelerator called the Crookes tube. So that's an electron beam. People spent years and years trying to push the energy of these beams from particle accelerators to ever higher energies. And so this is a machine that does that. This also uses induction. The electron beam looks like a loop in an induction coil inside of this machine. As they ramp the field in the machine up, the energy of the electrons goes up. And so they use this to make very high energy X-rays. This is a high energy electron machine. Next view graph, please. And this is one of the early radiographs of an imploding pit, where this is the edge of the pit that you can see along here. This is not super high quality data, but this really helped to make sure that this implosion was nice and spherical, so everything stayed round. Next view graph, please. Based on that work, the Raleigh experiments were problematic because they took these radioactive sources in the bottom of a canyon next to Los Alamos and they blew them up. When you saw that jet going up in the air, that's where the radioactive source was. That radioactive source went up in the air and it would sometimes blow across the road going to Los Alamos. They usually tried to have the wind blowing the other direction. The lifetime of that radioactivity was quite short. It was 8 hours or so. But still, they could detect radioactive fallout from those tests as far away as Texas. This was not a sustainable program for certifying nuclear weapons. And so in order to get the physicists who were working on this project to give up those kind of experiments, this new machine was built. It's called Fermex, and it's a high-energy X-ray machine, more like the betatron, but much higher intensity than the betatron. This guy, Douglas Venable, who came from the college I got my PhD from, University of Virginia, came up with an idea for how to build this machine, which was marvelously clever. So he could make very short pulses of high energy X-rays. The doses of the X-rays that he could make, to put them in perspective, were a couple hundred rad of dose, and he made that dose in about a half a microsecond. So a microsecond is a millionth of a second, a half a microsecond is half of a millionth of a second, and 200 rad of radiation is enough to make you sick, probably not kill you. 400 rad would probably kill you. So it's almost a lethal dose of radiation in a very short time. These X-ray machines are not useful for biological studies, but when you want to look through one of these implosions, it's very, very thick, and you need a lot of X-rays to see through it, to get anything out the backside. And then a marvelous fellow by the name of Glenn Say came up with a whole bunch of new X-ray techniques that made this whole new kind of X-raying work. Next view graph, please. That went along for a long time, from the 1960s until the 1990s. There wasn't really much use for X-raying these implosion-type experiments because the country had embarked on a big program of first above-ground testing and then underground testing. And so the way you could tell if a nuclear weapon worked is you would put it underground, you would detonate it, and you'd see a nuclear detonation. So the Fermex machine was used to do a lot of science, but it wasn't used so much for this direct stockpile nuclear weapons studies. But in 1992, the Comprehensive Test Ban Treaty was signed by Bill Clinton and a bunch of nations. And since then, there have been only illicit tests. It's only the North Koreans. The French did some tests, but not very many. And there aren't very many nuclear tests any longer. The problem is that nuclear weapons are complicated things, and as a function of time, they decay away, and how do you know they're still going to work? So people would like to be able to do experiments to tell that the nuclear weapons are still safe and they'll still work. That's called stockpile certification, and it's what Los Alamos does mostly nowadays. And so that raised interest in building a new, better radiography machine for doing these hydrotest experiments to certify the stockpile. And that led to the biggest X-ray machine that's ever been built, and it's 2 X-ray machines. It's called DART, the Dual Axis Radiographic Test Facility. It makes a dose of 1 kilorad, a meter back from the source, in times of 60 nanoseconds or so. 60 nanoseconds is 60 billionths of a second. So if you stood here when they fired the machine, you would die within a couple days. So this is, I mean, it's an enormous X-ray dose. But it's still not enough. Next view graph, please. So in order to understand how you can do the best possible radiography when looking through thick objects, you have to understand exponential attenuation. So I don't know if you're high school students or if you've taken algebra or calculus, but this is exponential attenuation. If you take a whole bunch of particles and you shine them into an object that just randomly scatters these particles away, then as they go through the object, the little red incident particles, which you can think of as X-rays, get scattered and they go away from the beam, and so as you go through, there are fewer and fewer left in the end. This is the number of particles in the beam plotted as a function of thickness. So if you have a thick object, you see fewer transmitted particles, and if you have a thin object, you see more. That's exponential attenuation. And that's described by Beer's law. If you take this Beer's law, if you have too much attenuation, you can't make an X-ray, and if you have too little, you can't make an X-ray. Next view graph, please. So if you take a thick object, which this is, and you try an X-ray with BBs that you shoot out of a BB gun, you can't see anything. You just see black on the other side. So that's not very useful. And then there are particles that you've probably had a talk about called neutrinos, and if you shine those in, they all come out the other side and you don't learn anything. So there's a perfect place in the middle, and these particles that come out of our accelerator that I worked at for most of my career are at the perfect place in the middle. The rate at which they remove particles from an incident beam is almost perfectly matched to making X-rays of thick objects. So that's why we started studying proton radiography, was to use it instead of X-rays for doing these hydrotests. Unfortunately, our accelerator didn't have a high enough energy beam to get the protons to go through these thick objects, but we could show the principles of proton radiography. So next view graph, please. The problem with charged particles is that they're not rays. X-rays are neutral particles, and so they're indeed rays. They go on perfectly straight lines until they collide with an electron around an atom and get scattered. Charged particles, all of these things that were called rays, these electrons, the beta rays that come out of here, which are also electrons. Oh, by the way, it's time to come up here and look. So here's the electrometer that was next to the uranium plate, and you can see what's happened to it. All the charge has gone off of that electrometer, and this electrometer is still charged up. It's still pointing out. So that's how Marie Curie measured radiation and discovered new elements and started the field of nuclear physics. So that's a simple radiation detector. Isn't that marvelous? Okay, so back to this. So now you could go sit down again. I just didn't want to miss the discharged electrometer. Charged particles have the same forces on them as you see on this electrometer. When you have two charged particles next to each other, they push each other apart. If they have the same sign, they suck each other together if they have different signs. So if one's positive and one's negative, they attract. So in material, you have electrons, which are denoted here as the little blue dots, and you have nuclei, which are the big green dots. Both of those things are charged. But the atomic nuclei is a very heavy thing. It has all the mass of the universe that we know about. Doesn't include dark matter, is in atomic nuclei. That's why they're important. Everything that you weigh on a scale, These electrons are just little light things. These nuclei are heavy things. When a charged particle tries to go through matter, it's going very fast, so it goes through the matter, but the electrons get sucked towards it as it comes past, and then they go away. That takes energy out of this particle, but it doesn't change its direction. So it causes these charged particles to slow down and eventually stop. Since we've got, if you take a column of air that's a square centimeter, so 0.4 inches by 0.4 inches, all the way up through the atmosphere and you weigh it, it weighs a kilogram. That kilogram of air above us is very important because when these cosmic rays hit the upper atmosphere, it slows them down, and so the dose that gets down here is much reduced. Otherwise, there would be a lot of radiation, and we wouldn't do so well, I don't think, as a species. Atmosphere is important. That's because of the electrons in the atmosphere. Now, the nuclei in the atmosphere do something else. Occasionally, they collide. The charged particle collides with one of these nuclei, and then a nuclear reaction occurs, and that takes the charged particle away. So when these pions in the upper atmosphere are trying to, or the protons are trying to come down through the atmosphere and hit us, irradiate us, and make us sick, the atmosphere filters out all of the particles that have nuclear interactions because they collide with nuclei and they go away. And the particles that are left over, which are the muons and the electrons, all slow down, and so a lot of them go away before they get to the surface of the Earth. This is a good thing. But as you see, this electrometer is also discharging, and it's discharging partly because of cosmic rays, partly because of natural radiation. And in this experiment here, I showed you the cosmic rays and the natural radiation. And a lot of the natural radiation is here because cosmic rays have hit the Earth and they've induced radiation in elements in the walls and the concrete and around us. But some of the radiation has been here ever since the Earth was formed because it comes from uranium. Okay? So those are the ground rules of my talk. Next view graph. So we knew in Los Alamos that these protons had enough penetrating power to go through thick things, but we also knew that doing radiography with them was going to be hard because when they go through material, they don't come out on straight lines. So you can't, if you try to make a picture of an object with a detector that's located away from the object, you just get a blur. Next view graph. This detector measured particle positions, and so you could calculate where the particles came from the object, and this object said Lannel PRAD. It was some still plates that were machined. Next view graph. What we discovered, invented, was that you can take these charged particles, and I made a mistake tonight. I wanted to show you this. If you take a magnet and put it next to this tube, the beam bends. And so you can build a lens for charged particles by using magnets. So if you put a lens between the object and your detector and you focus the charged particles, you can get an image. For the kind of radiography Los Alamos does, where you want to make this image very fast because the thing you're looking at is exploding, it's important that you get all your particles at the same time. You can't do this nice thing of measuring each one and projecting back. This lens was very important. This makes the charged particle radiography work. And so we've used this to study explosions and the science of exploding things in Los Alamos. Next view graph. This is our accelerator. This is on a mesa. This used to be called the LAMF accelerator, which stands for Los Alamos Meson Physics Facility. And now it's the LANCE accelerator, which is the Los Alamos Neutron Science Center. It's a long linear accelerator, and it makes protons that are 800 MeV. And where we do our work is buried under a mound of dirt here called Area C. It's a dome that's covered with dirt for radiation shielding. Next view graph, please. We use a lens to take protons. We shine protons through an object, and we use the lens to image the object on a detector. This is where we do our explosive experiments. This is a big steel sphere. It has 2-inch thick walls, And we're allowed to blow up to 5 pounds or so of high explosives in here. These orange things are our magnets that make the lens. It's not as simple as a glass lens. These are called quadrupole magnets. And this place here is where we put this detector. So this is a detector, it goes there, the object goes here. And since we don't have enough energy to look at things, thick things, we have to look at thin things. So we've discovered, next view graph, that if we put a collimator in the middle of the lens, that makes this system ideal for looking at thin objects as well as for looking at pretty thick of objects. Next view graph. We do experiments like this one. This is high explosives. This is high explosives, and this is high explosives. The yellow-colored high explosive is a special kind of high explosives. It's called PBX 9502. And it's very good for nuclear weapons because it's insensitive high explosive. If you take this explosive and you have it in your hand and you drop it on the ground, it won't explode. If you drop it off the ceiling up here, it won't explode. It's very hard to get this explosive to detonate. So it's exactly what you'd like to have in nuclear weapons because it's safe. It's not so good a high explosive because when, you can see that in this experiment here, that when a detonation wave moves up through it, if the detonation wave has to turn around, this is a detonation wave, and the left side of the picture shows detonation waves moving through an explosive. The right side of the picture shows a calculation. When this detonation wave comes up through a narrow stalk into a fatter stalk, it has trouble turning around the corner. And this bright spot here, which is high explosive, which gets compressed, it doesn't detonate. It turns out that that depends on a whole lot of things. It depends upon how you initiate. Over here there's a wider stalk, and there's a smaller region of this explosive that doesn't detonate. We've done a lot of experiments to try and understand this process better, and they've turned out to be very important for assuring that weapons that are built out of this very safe high explosives continue to work and are safe. Next view graph, please. Another kind of, we've done a lot of experiment. We do 40 experiments a year, and we do all sorts of different things, but I'm not going to bore you with a lot. But I'm going to show you this one. This is in 1969. That was during the Vietnam War. There was an accident on an aircraft carrier, and John McCain was part of this accident, and I'm not quite exactly sure, the presidential candidate. A jet crashed on the deck of an aircraft carrier, and it was loaded with bombs, just conventional bombs. Those bombs were designed so that they should have been safe in a fire, but they weren't, and they started to detonate. As the fire took off, bombs started detonating, and this wound up with a lot of people killed and injured, and tremendous damage to the top of the aircraft carrier. And that's because people don't have a good understanding of what happens when you take the high explosive that is in bombs and you heat it up. So we've done experiments to study that. Next view graph, please. And this is the experiment. This is just a little piece of aluminum with high explosives in it that are very slowly heated. Now, high explosives have this feature that when you heat them up, when you get to a certain temperature, then they take off heating themselves, and you don't have to heat them any longer. And as they heat themselves, they cook off. They eventually start to release energy very quickly. They don't detonate like a high explosive detonates, but things blow apart. So this is, you can see the container here blowing apart. This is looking at an experiment looking from the side and an experiment looking from the front. Next view graph, please. We discovered for different kinds of high explosives, different kind of mechanisms for how this chemical reaction takes off. In this one, you can see what happens is you develop a hot spot in the middle and it cracks the explosive, and then the burn of the high explosive moves out through those cracks and it releases energy very fast. So we can measure how fast the energy comes out. From this, the chemists who designed this experiment have built a new model to describe this cooking off of high explosives and to make conventional weapons more safe. So you can now design weapons that will have less likelihood of cooking off and accidentally exploding in accidents involving fires. Next view graph. So we studied proton radiography for these kind of experiments where we drive things with high explosives and they occur very fast. While we were doing that, we thought, wouldn't it be marvelous if we could use these charged particle interactions to radiograph things, but not use protons? Because when we do these experiments with protons, the things we radiograph become radioactive because of nuclear reactions. These cosmic rays, which when they get to the surface of the Earth are mostly made up of these muons, are very good in this regard because muons have no nuclear interaction. So they don't make things radioactive. They're charged, so we can still do the same kind of radiography as we did with the protons. So this shows you how cosmic rays get to the ground through one of these cascades in the upper atmosphere, actually here, and then the particles make it to the ground. This is the dose as a function of the thickness of the atmosphere. Next view graph, please. Oh, and primarily what reaches the ground are muons. They reach the ground because they have a long lifetime. Doesn't seem so long. It's 2.2 microseconds, 2.2 millionths of a second. But compared to pions, it's long. Pions only have a lifetime of 26 billionths of a second. They only interact through the Coulomb force and something called the weak force, which is so weak that you can generally forget about it unless you're a physicist studying neutrinos. And because of that, and they're very energetic, so they go through a lot of material. They go through many meters of rock. Next view graph. The number is not great, and you can see that over here when I turn my muon trigger on. That's the number of muons that are going through these tubes. You can see every individual one. So the number of muons that get to the Earth are 1 per square centimeter per minute. So there aren't very many. That's caused us a lot of problems because when we said we wanted to do radiography with these muons, they've said, we know you can't do it very fast because of this experiment. Next view graph, please. Physicists always dream of finding gold. So this is the inside of a burial crypt. It's actually a museum view of the inside of a burial crypt of an Egyptian tomb. And the stuff that looks like gold in here is all gold. In Egypt, there's a lot of pyramids, and they haven't been all that well studied. And looking inside of them has been kind of hard. Finding the burial chambers has been hard, and nobody's sure they've discovered them all. So in the 1960s, next view graph, please, a set of physicists, one of them very famous, Luis Alvarez, went to Egypt with some detectors that weren't too different from these. He had things called spark chambers and put them in the burial crypt that was known in this middle pyramid here and took data measuring the direction the cosmic rays were coming through the pyramid to try to radiograph this pyramid and look for potential burial crypts that nobody had seen. The data that he took showed that there were no burial crypts in this pyramid that were larger than about 1 meter by 1 meter. So unfortunately, he didn't get rich by finding gold. Physicists never get rich by finding gold, but we always try to find new ways to look. But this experiment took a whole summer's worth of running. And so, but it used this feature of the cosmic rays stopping as they go through this material. And so it's not well suited to looking for things that aren't very thick. Next view graph, please. And I guess you have to hit it again. So we want to go back to this interaction, the Coulomb interactions of these muons. What we decided to try to do is to, instead of waiting for these muons to stop so that we can only use the very few that stop, we would do radiography by measuring the Coulomb interaction, by measuring how much the angles of these muons change. That's how we use the protons in Los Alamos for our proton radiography.
You can't stop them. You need to change tape.
Oh, sure. Okay, so we started studying muons because we wanted to radiograph things to not make them radioactive. And then 9/11 happened when the World Trade Centers got blown up and fell down. And people became very concerned all of a sudden that if terrorists had a nuclear weapon, they could destroy a large part of a city and kill millions of people instead of thousands of people. And there was no defense against a nuclear weapon being shipped across our borders. It turns out these muons are ideal for looking for hidden nuclear weapons, and I'll show you that. Next view graph, please. We decided to measure the angle of muons going into a volume and the angle of muons going out. So the angle change, and when you put something that's built out of heavy materials like uranium, they scatter the muons a lot more than light materials like iron in the middle. And so we got together some old apparatus and we showed that this was true. So these are old detectors like these detectors for measuring particle positions so that we could use cosmic rays and look for this piece of metal in here, which is tungsten, which is a heavy metal that's not so different in properties from uranium, except it's not radioactive. And these are the experimental pictures we made of that piece of tungsten using this angle change of the muons. Whoops. And next to it was a calculation. So our idea is to use these muons to look for nuclear weapons that are in somebody's trunk. Next view graph, please. So the idea is shown by this movie here. This is my Ford Explorer, which I drove down here, and this is my simulation of muons going through my Ford Explorer. Now, if I had a hunk of uranium big enough to be an atomic bomb in the back seat of my Ford Explorer, then, next view graph, when the muons go through the uranium, they bend by a big angle. So if I measure the angle coming in and the angle going out, then I can tell that there's something heavy and big that's potentially threatening in the back of that guy's Ford Focus. And so I can grab him out of the Ford Focus and interrogate him and find out what he's doing. Nobody believed we could do this, but we did some experiments. Next view graph, please. With an apparatus that looks like this, but this isn't the one I expected to see. Next view graph. Yeah, keep going. Yeah, we built a muon tracking device where these detectors up here measure the angles of the muon coming in, and these detectors down here measure the angles of the muons going out. This is me laying on a little makeshift mattress with a book, and I sat in this device for about a half an hour, and then this is the tomograph. This is a slice through me that we made after that half hour of data, and I had this little piece of lead in my pocket, and so you can really tell the difference between the piece of lead and me. So the next view graph. Then we went on to do tests where we hid objects. This is that slug of tungsten you saw in the previous view graph in a barrel of sand, and these are slices of a tomograph made using this natural radiation to locate the tungsten object inside this barrel. This data got a company excited enough about this technology that they had us build them a scanner. Next view graph, please. This is the scanner consists of 2 layers of detectors. So we just went to a little conference. These are the people who went to this conference at this company where we all gave talks on this technology of muon tomography. And we decided to take a conference picture. So this is a picture of all the participants in the conference, but we're standing inside the muon scanner. Next view graph, please. And after we stood there for a few minutes, this is the picture of people standing in the scanner. The interesting thing is that big heavy guy, he's this big heavy blob back here. If you take a slice through him, you can really tell that he was a big heavy guy. So this technology really works. So next view graph. That gets me to the end of my talk. So radiography is an example of people doing abstract research. I mean, research that they're just doing to think about new things. That right away discovered X-rays and invented X-ray radiography, Röntgen did. Immediately, it was put right to use. You've seen over here, these are Nobel Prize winning experiments if you did them 100 years ago, 110 years ago. They're simple. So important experiments in physics are often simple, and it's experimentalists playing with apparatus. You don't have to be really smart to do this kind of stuff. You just have to be persistent. A science career is fun and can lead, it can lead to things that you never dreamed of when you start doing these kind of experiments. And when you discover one of those things that you never dreamed of, it is really exciting. So if any of you go into science, that's a great thing. You'll have a lot of fun. Thank you.
Thank you, Chris. Anybody have a question or two?
Yeah.
Did the Frenchman who shared the Nobel Prize with Marie Curie, you said that there was uranium in the phosphorescence or something like that?
Yeah.
Did he know there was uranium in it?
Well, he knew he had uranium salts that were phosphorescent. And so he figured out pretty quickly that what blurred the film was coming from the uranium.
So those folks knew what uranium was before there was...
Yeah, they had uranium, yes.
Is phosphorescent stuff in the ocean radioactive? Is that...
No, I mean, chemicals that phosphoresce are just chemicals that have atomic energy levels that you can excite, and they emit light when they decay. And some of them emit the light, they stay up here in the excited level for a while, and so you can excite them. If you take a UV light and you go out and you shine it around, you'll see things that glow. Okay, that's fluorescence. And those kind of things are useful for measuring radioactivity, because radioactivity is like the fluorescent light. It excites atomic energy levels, and then the material glows. But uranium is radioactive. Now, these plates, this is Fiesta ware, and that's what uranium was mostly used for before World War II. After World War II, you couldn't get uranium any longer. So Fiesta ware had to make their pigments out of other colors. But you can buy these on eBay, and they're kind of a collector's item nowadays.
You also said that there was some, I forget, but in connection with one of the experiments, that there was uranium from the origin of the Earth.
Yeah.
That's just because uranium is an element?
Uranium's an element, and it was made in supernova explosions after the Big Bang. The first generation of stars, there was no uranium, but then they blew up, and when they blow up, then you make heavy elements. It's hard to make heavy elements.
Is that true of all the elements, or just
That's true of all the elements that are heavy. I mean, there are different processes, and I don't know, Bob can probably help me here. I mean, but all of the heavy elements have to get made in explosions. Up to somewhere, calcium, you can build these elements up in stars, but then you have to make things very fast, because you have to make unstable elements, and then you have to build up neutrons. So you have to make things that are unstable, and then you have to add neutrons to them, and they need to decay and become stable and add neutrons, and that takes supernovae to do that.
when you say you're talking about nature, right?
Nature,
Evolution.
yeah, nature. Whoever it was who did all that stuff. Yeah.
Madame Curie got very sick and died.
She died, but she was quite old. She was in her 70s. She died of aplastic anemia. Both she and her husband suffered. Her husband studied radiation burns. She discovered radium, and she made radium. And the way she made radium is you take a bunch of uranium, and the uranium decays. I think it makes radon, and the radon decays and makes radium. And radium's a metal, and so she had this big farm, and she would go out and harvest the radon, and she'd have to do the chemistry to get the radon out of the pitch blende ore. And when she did that, and it was at a rate of every couple of months, she would get ill from the radiation, and then she'd get better. And she did this for a large fraction of her life. But I think they think that where she got her biggest radiation doses was during World War I. They travel around the battlefields with X-ray sources, radiographing soldiers, and they use doctors nowadays use shielding and protect themselves from the radiation. But they knew radiation was harmful, but it was new, and they,
Any other questions?
So when you handle that uranium painted
plate.
plate, is that you pick up?
The radiation level from the uranium plated plate is very low. And so the government has studied this and declared these to be totally not hazardous, and so they're not controlled. It's, the levels are measured in the millirem right next to the plate, so they're low levels of radiation. It just is I don't know how Fiestaware works in microwave ovens, so it'll work fine.
Okay, let's thank Chris, and we want to go up